Good afternoon, everyone. Thank you for joining us again for our next seminar in our series. You might recall we're having research talks from our early career audience this year. Today, I'm pleased to have Adam Thompson give a talk for us. Adam has listed, I suppose, his affiliation as UQ, although I guess technically he's not affiliated at the moment because he's just finished his master's at UQ and he's flying to Germany next week to start his PhD there. Adam has agreed to talk to us on Harmonic-Einstein metrics on Riemann surfaces and Higgs bundles. Thank you very much, Adam.
Thank you, Tim, for the introduction, and thanks for inviting me to speak. Yeah, as Tim said, I'm leaving the country next week, so it's nice to have this opportunity to kind of wrap up what I did during my master's thesis and speak on it today. Yeah, I did debate whether to put the UQ there or to put the Münster there. I thought it would be a bit premature, so I stuck with the UQ. Okay, so I'll get started. So just to briefly outline my plan today, I acknowledge that maybe harmonic maps are slightly familiar to some people, but not completely familiar to everyone. So I'm going to start off with just going over those, and hopefully if people do know, it'll be a nice leisurely start. And then what I want to do is introduce kind of the main object of study for me today, and that's this so-called Harmonic-Einstein equation. After that, I guess the main interesting thing, in my opinion, about what Ramiro and I have done during this project is find a link between this Harmonic-Einstein equation and something called Higgs bundles. So these are an object that were introduced by Hitchin in the 80s, and they're very popular to study. And so this link is kind of in line with the kind of research people in this Higgs bundle field do. And I think it's quite nice and has some good applications. And so then I just want to finish off and talk about an application of this to something that's a bit closer to home for Ramiro and I in terms of what we're interested in mathematically, or what we started out with looking for, I should say. And so just to kind of preempt where I'm going with the talk, I'll say that the main theorem that I'm looking to work towards today establishes this correspondence between solutions to these so-called twisted Harmonic-Einstein equations. And so I'll go through, of course, and explain what these mean, and with gauge equivalence classes of these Higgs bundles. And so the beauty of this link is that the Higgs bundles, hopefully we have a better understanding of and know what the solutions there look like. And so we can then take that knowledge and apply it to these Harmonic-Einstein equations. Okay, so like I say, I'll get into it. Okay, so what is a harmonic map? So the setting I want to work in today is I'm going to take two Riemannian manifolds. I called one sigma, I call the other n, and I'm going to look at smooth maps between them. Now, the harmonic map condition is what I've written here. So there's this natural covariant derivative that I can apply to the differential of this map. I've written this over here on the right. So essentially what it's measuring is how much h, or the differential of h, commutes with the respective Levi-Civita connections, if you like. And then we can trace this and set it equal to 0. Okay. And so why might you do this? Well, it kind of unifies a load of classical geometric equations. So I have some examples down here. So if I took my target manifold to be the real number line with just its normal flat metric, I mean, we don't have much choice there, then this harmonic map equation is just precisely what you would expect it to be. It comes out to be the classical Laplace-Beltrami of h is equal to 0. Okay. the second kind of natural equation that appears here is if my domain is one-dimensional. So since I asked for it to be closed, and I'm going to tacitly assume that it's always connected, this forces me to have S1. And then this harmonic map equation becomes precisely the condition that H, or the image of H more precisely, is a closed geodesic. Okay, so this is, of course, another natural equation in Riemannian geometry. And then the third one is if my H is an isometric immersion, and I look at the image of sigma in N, then this harmonic map equation becomes precisely the equation for this image to be a minimal submanifold when it has the induced metric. Yeah, so this harmonic map equation has been studied for quite a while. So it was originally introduced by Thompson, and like I said, it unifies these kind of natural geometric equations. So it's been well studied. Maybe just some more background information. Just like the classic equation for harmonic functions from Riemannian manifolds, it arises as an Euler-Lagrange equation. And to get the energy, it's essentially the same as when the codomain is R. We just have to define the norm of dH using the metric on N. And so the way we do that is, well, using H, I can pull back the metric on N, and then I trace it with respect to this metric on sigma. Okay, and this gives me an energy, and the harmonic map equation is precisely the Euler-Lagrange for this. And a second useful bit of information is that the existence theory is the best when the sectional curvature on my target space is non-positive. So the kind of classic method to prove existence is a heap flow method, and this works the best when we have this non-positive sectional curvature. Okay, so this is the harmonic map equation. Now, actually today, I want to consider just a slight generalization of this. And this is the so-called twisted harmonic map equation. So it's exactly the same, or almost exactly the same as before. The only extra data I'm going to add here is, firstly, H is going to come not from my manifold of interest sigma, but instead from its universal cover. And secondly, I've added in this extra bit of data, which is a homomorphism from the fundamental group of sigma to the isometry group of the target manifold. And so here I'm going to, from now on, assume that this target manifold is complete and has non-positive sectional curvature. And then the correct thing to do in this case is I require, of course, my harmonic map equation. And I'm also going to ask now for H to be rho equivariant. Okay. And so in what sense is this a generalization of this previous equation I had? Well, if this rho's image lay inside some compact group of isometries, where I assume that this quotient, everything works out nicely and it's smooth, then this is actually just the same as the harmonic map equation between two compact manifolds. Okay, because in that case, any smooth map between the compact manifolds, I could lift to a map between the universal covers that's equivariant for the induced representation on the fundamental group. Okay, so this is a genuine kind of generalization of this classic harmonic map equation between compact manifolds. Okay, so we have this slight generalization. Then, of course, it's important to know, well, there's a good existence theory for the classical harmonic map equation when the target had non-positive sectional curvature. Does that remain true in this twisted case? And thankfully, it does, with the slight caveat that you need a condition on this row. So I'm not going to tell you this condition explicitly, but it does. There is one there that exists, but it's an if and only condition. So we know precisely in what instance these harmonic maps do exist. And so, as I said before, the proof is by a heat flow method. So I start with an arbitrary row equivariant map, and then I try to deform it to get something that satisfies this harmonic map equation. Okay, and so like I said, I'm not going to define this condition on rho, but what I would like to do is just give you this picture of the behavior that we have to be careful of. Okay, so here I'm imagining, sorry, this H should be from R, should be Z equivariant, say. So here, because the image no longer has to be compact, essentially what this condition on rho is trying to do is rule out, as I evolve this H to try get my harmonic map, that it just goes off to infinity and disappears. So the condition on rho says essentially that the image of H of t remains within some compact set independent of t. Okay, and with that we get this lovely existence theorem. So we have these and we have them to play around with. Okay, so that's twisted harmonic maps. Now, as I said, my main object of study today, what I really care about are these so-called twisted Harmonic-Einstein equations. Okay, so I keep these assumptions on my target, and maybe naively, what I would do is I have my harmonic map equation, my twisted harmonic map equation, more precisely, and then I have the Einstein condition on sigma, that my Ricci curvature is a multiple of the metric, and I would just say, okay, these are two equations, I put them together. But the problem with this is the first equation, the twisted harmonic map, certainly relies on the metric G sigma, but this second equation, the Einstein condition, has no reliance on the twisted harmonic map equation. So if I do this, then essentially what I'm asking you for is to find an Einstein metric and then find a harmonic map out of it. So somehow we need to couple these equations. And the way we do that is I add essentially the only thing I can to the right-hand side of my Einstein equation. And that is I pull back the metric on the target using H, and then I add this to that equation. Okay, so if I pull back a metric, then I get another 0,2 tensor, so this makes sense. Now you might be asking why one might do that, and I think given these two equations are so ubiquitous in geometry, then it just has independent interest. But as I said, for Ramiro and I, we had ulterior motives that I'll talk about at the end, and so this does kind of arise naturally in geometry. Okay. Perfect. And so just to give you a small example of a solution to these. So if I look, I said before that a closed geodesic gives me a harmonic map from S1. So again, perhaps if I want to think about the twisted case, then I should be looking at a map from R into N that's Z equivariant for some map from Z. but I'll just say from S1 here. And then these are also, these we can also look at solutions of the twisted Harmonic-Einstein equations.
And I've got a question, if you don't mind.
Yeah.
Looking at this twisted harmonic equation, like roughly speaking, when you go in to try and solve this equation, what are the things that you're supposed to know ahead of time, and what are the unknowns that you're trying to solve for? Like how much data are you supposed to prescribe ahead of time here?
Okay, sorry. Yeah, I should have said this. So the prescribed data, prescribed, is, so this NG, the target manifold, and technically the row should also be prescribed. And so then you're trying to solve, what we want is this pair, G sigma, so the metric on the domain and H. Okay.
Okay, yeah, thanks.
Yeah, I mean, when it actually comes down to looking at it, somehow it's useful to also to think of it as we're trying to solve for a triple, where it's the metric on the domain, the H, and the row. But I think somehow, yeah, really the row should be prescribed. So if you,
row is sort of like discrete data, isn't it?
so I think the right way to think about row in this case is when you're talking about the classic harmonic map equation between two compact manifolds, then you need, often something you do is you prescribe a homotopy class and you want to find a harmonic map within that homotopy class.
Yeah, okay. So this takes that
Okay.
off.
Yeah, the row is somehow analogous to that, prescribing the homotopy class.
Okay, great. Thank you.
No worries. Okay. Yeah. Okay. Yeah. So with the circle, we had the harmonicity, and then the equation for the metrics is just another manifestation of saying that this is a unit speed map. So it's a cute little thing to play with that and show that. Okay. Yeah. So that is the twisted Harmonic-Einstein equation in general. And so obviously the title of my talk, I don't want to look at this in general. I want to look at some special cases where I can start to get hands-on solutions to these and have some hope of solving it. I mean, of course, in general, it's a more general version. It includes, as a subcase, perhaps I should say, the Einstein equation. So there's clearly no hope for me yet of solving that in general. But perhaps if I look at some low dimensional domains, I have some chance of solving these. Of course, the lowest dimension I could look at is a one-dimensional domain. But this example I just gave is essentially all of the examples coming out from one dimension. And so then the next dimension up is the Riemann surface case. And so this is the first non-trivial dimension. So this is what I decided to study in my master's. Okay, so the setup here is, now I'm going to take my domain, this sigma, to be a Riemann surface, and I'm going to ask for the genus to be greater than or equal to 2. So we could look, of course, at the genus 1 or the genus 0 case, but I'm not going to focus on that today. I mean, in particular, for the genus 0 case, if you're looking into non-positive sectional curvature, then you're not really going to get anything interesting. And I'm also going to specialize my codomain. And so I'm going to take my codomain here to be this symmetric space, SLNR mod SONR. And I'm always going to give it this symmetric metric. And so really, you could think of this in different ways. you could think this is just a good example to keep in mind, but it's also motivated by a broader context. Okay, and then also my rho should go into the isometry group of this symmetric space. I'm going to take it here into SLN-R. Okay. Okay. And so then my first observation in this case is actually the Riemann surface case for harmonic maps is the critical dimension. And something very special happens in that the harmonicity no longer relies on a metric, but is actually a property of a conformal class of metrics. Okay, so that is to say, if I have a harmonic map out of a Riemannian surface, and I multiply the metric by a positive function, this domain metric, then my map remains harmonic. So all I really need to care about is the conformal structure. Okay, and then if you remember my existence theorem before, so there were several names there. In particular, I'm going to use the result of Corlett. Then given a conformal class on my domain and a good rho, so this is a rho satisfying the correct condition, then there exists a unique twisted harmonic map coming out of this Riemann surface with this given conformal structure. Okay, so I call this H sub C. And then my second observation is, if I recall, on a Riemann surface, of course, I have that, my Ricci curvature is going to be always a function times the metric, namely the Gauss curvature times the metric. And so combining that with the fact that, of course, mean minus G is a function times the metric, I have that H should also be weakly conformal if it's to satisfy my Harmonic-Einstein equation. And so by this, I mean that the pullback of the target metric by H is some non-negative function times the domain metric. Okay, and so the reason I say weakly conformal here is that this function might have zeros. You know, the pullback's not a genuine positive definite thing, but it is non-negative. Okay, so these are some useful observations to start with. And so maybe based on the fact that we know on a Riemann surface within a conformal class, I can always solve my Einstein equation. There's some hope here, and that hope is actually well-founded. So the first thing we can prove is that those conditions are also necessary. Sorry, not necessary, sufficient. Should send me back to first year logic. So that is, if I'm given this harmonic map coming out of my Riemann surface, and it solves, and it's weakly conformal, in addition to being harmonic, then there's a unique metric within this conformal class solving the Einstein-like equation on the base. And so what that tells me is that my twisted Harmonic-Einstein equations, in this case, reduce to finding weakly conformal harmonic maps coming out of these Riemann surfaces. Okay, so if I fix C, all I have to worry about is finding a harmonic map that's also weakly conformal. And then I know I can change my metric within the conformal class to get this base equation. Okay, so that's a really nice reduction of this problem here. And so then, yeah, we're left looking for these C such that when I apply Corlett's theorem to get this harmonic map coming out, then I'm also weakly conformal. And that gives us, there's kind of two approaches now to follow. So the first approach is kind of what I alluded to before. So in this one, we vary C. What this is based on is this map in Collette's theorem is weakly conformal if and only if C minimizes this functional. So this functional here, what I've done is I've taken the energy that I said define harmonic maps, but now I'm viewing it as a functional on the conformal structure. So as I vary the conformal structure, I always get a unique harmonic map out. And then I look at the energy of this harmonic map. And I think this result goes back to Schoen-Yau and Sachs-Uhlenbeck, that if C minimizes that, then it's harmonic and weakly conformal. And so in this direction, the result of Francois Laborie says that if this rho is something called a Hitchin representation, then such minimizers do in fact exist. Okay, so that gives us already plenty of examples there. So that's quite nice.
Sorry, excuse me. You said that result went back to Shane and Yao, and who else did you say?
Sachs and Uhlenbeck.
Oh yeah, Saxon, right.
Yeah.
Thank you.
No worries. Okay. But what Ramiro and I found is that actually there's a second approach, and yes, this is the main crux of what we did. And so this leads us to the Higgs bundle point of view. And so what this approach is that now we view this rho not as being a map from the fundamental group into SLNR, but instead view it as going into SLNC. Sorry, so yeah, on the top, you can see I have what our goal is. And what this opens up for us is that these maps into SLNC, or if you can see, we have to take a special subset. I've denoted this by plus, up to conjugation. So this quotient is conjugation. There's a correspondence called the non-abelian Hodge correspondence of this set with something called the moduli space of Higgs bundles. Okay, and so our approach is to try utilize this correspondence to see if knowing something on the Higgs bundle side can help us identify when these harmonic maps are also weakly conformal. And so the way this works is you can view the correspondence like this. So the rho by Corlett and Dollinson, we said that given this rho from the fundamental group of sigma to SLNR or SLNC works just as well. We can cook up for a given conformal class a harmonic map. Let's see here. And there's always a fixed conformal class on my Riemann surface. And then the non-abelian Hodge correspondence says that these are also the same as something called a Higgs bundle. And what a Higgs bundle is it's a holomorphic vector bundle with this so-called Higgs field phi, which I've said lives in this strange looking space. But all this means is that it's a matrix valued, or locally, it's a matrix valued one form that when I write it in terms of complex coordinates has only dz. So it looks like phi equals some matrix. This depends on z of dz locally. And there's a holomorphicity condition. Okay. And so on the surface of it, perhaps this doesn't buy as much, but the key point here is that if we trace through how this correspondence actually works, it's that our map H is weakly conformal if and only if, when I square the matrix part of this Higgs field and trace, I get something that's identically zero. So it vanishes identically on my Riemann surface. Okay. And so the benefit of this is when I'm talking about taking a row and cooking up a harmonic map using Corlett and Donaldson's theorems, I don't have much knowledge of this harmonic map, and it's not at all clear when it's going to be weakly conformal. Whereas on the Higgs bundle side of things, it allows us to pinpoint precisely the ones that turn out to be weakly conformal. And so these Higgs bundles have also been very well studied over the past 40 years, maybe. And so there's many instances where this Dolbeau, this Higgs bundle moduli space is very well described, and we can kind of leverage this to our advantage. And so to give an example of that, if we specialize to the case, sorry, I said n equals 2 here, but I'll just clarify what I mean by that. Rank E equals 2. In the rank 2 case, there's a very explicit parameterization of these Higgs bundles, where I again remember that originally I cared about things going into SL2R. That goes back to Hitchin. So essentially what Hitchin's parameterization says is that I take this rank 2 Higgs bundle, then I look at the zeros of phi, the Higgs field, so where it vanishes. Now that, since phi is a holomorphic object, there's only finitely many. And in fact, there's an upper bound on the number that can occur. And then you also look at this trace phi squared appearing again. And that gives a parameterization, the moduli space. And so conversely then, if you were to give me a set of points that's not too big, give me a function, then I could give you a Higgs bundle back with those two things. And so in particular, this works for trace phi squared equal to 0. So that's precisely what I wanted. And so in that case, those satisfying that condition are just given by specifying the zeros of the Higgs field. Okay. So from this description of the moduli space that Hitchin gave, we get this following description of these solutions to our twisted Harmonic-Einstein equations. And so on the left-hand side, so it's just convenient here to fix this integer r. So sorry, this should be r as an integer, I'll say. And as you can see, there's this upper bound on how big it can be based on the genus of our Riemann surface. This is genus of sigma. Okay. And so then we can say that the solutions to the twisted Harmonic-Einstein equations, in this case, where the differential of H has precisely 2 R zeros, is given by some covering space of the symmetric product of sigma with itself. So you can think of this symmetric product of sigma with itself 2R times as a point in this is just a subset of sigma with 2R points. Okay. So essentially what we can do is parameterize solutions to these twisted Harmonic-Einstein equations by the points at which the differential of H vanishes. And then conversely, if you want to prescribe the points at which differential of H vanishes, then you can find a solution of the twisted Harmonic-Einstein equations, in this case, where that happens. Okay, so that's quite nice. And so then just to go on and speak quickly about an application of this. So here, again, I stay with my closed surface where the genus is greater than or equal to 2. And I take rho, which is homomorphism from my fundamental group. Then I can form this flat vector bundle over my Riemann surface. So here, this is an associated bundle to the universal cover of my surface. And so necessarily, there's an inequality called the Milnor-Wood inequality that says that the Euler class of this vector bundle is bounded by G minus 1. So this was actually by Milnor, would generalize this in a particular direction. So to give you an example, not over a Riemann surface, but just over S1. So here I have the base, which is S1 in this case. There's these R2 fibers. And what this rho gives me is the monodromy of the flat connection on this vector bundle. So in this S1 case, if I start at this point over here, and I pick a point on the fiber above it, now I parallel transport around my S1 base. Then I come back possibly to a different point, but this rho tells me exactly that change there, you know, how my points change as I parallel transport around a loop in the base. Now, if I take one of these vector bundles and I specify a metric on my base and a rho equivariant map coming from the universal cover of my base to SL2R mod SO2R. So the significance of this is SL2R mod SO2R parameterizes inner products on R2 with a fixed volume form. So if I take these two, then I can actually cook up what I call an invariant metric on this vector bundle. So it's not invariant in the sense that there's a global R2 action, but if you look locally, there is an R2 action. So it's morally invariant, but there's not quite a global action there. And so the way we cook up this metric is locally, you can pick coordinates that look like an open subset of sigma times R2. And then in these, my metric is just this product. So I take the metric I specified on the base and just this metric on R2 determined by my rho equivariant map H. So of course, H goes into SL2R mod SO2, so there's some ambiguity there. It's not a proper matrix, but since I only care about the symmetric part, that doesn't matter. Okay. And so then the significance of this, or why we originally looked at the Harmonic-Einstein equations, is that if I cook up metrics in this way, on these flat vector bundles, then if I have a solution to these Harmonic-Einstein equations, then I can find a metric that solves this so-called Ricci soliton equation. So what I mean by that is there also exists an X such that the Ricci curvature of this invariant metric on M is equal to -1/2 G plus some Lie derivative term. And so really for Ramiro and I, this is how this originally started. that we were studying these invariant Ricci solitons. And so the twisted Harmonic-Einstein equations arise really naturally in that context, so as a dimensional reduction of that under a particular type of symmetry. And so I didn't have time to talk about the converse, but I just wanted to mention here that with some assumptions, the converse is essentially true. So if you have one of these Ricci solitons that has a particular type of symmetry, then it's actually coming from one of these solutions to the twisted Harmonic-Einstein equations. Yeah, so there's some technicalities there that I haven't mentioned, but that's true also. So in this case, that really is the Ricci soliton equation in this particular context. Okay, yeah, so thanks for listening. I know, sorry, I'm a little bit early here. I took this from a board talk and I made it into slides, so I wasn't sure how long it would go for. I'm glad I made most of the time, but thank you for coming.
Thanks very much for that talk, Patrick. Sorry, Adam. Does anyone have any questions for Adam? I'll ask some questions. Yeah, so Ricci flow applications of your Ricci solitons, what are the asymptotics of these guys? Are they collapsed, non-collapsed? Are they likely to arise as useful in modeling recovery of Ricci flow after surgery?
So perhaps what I'll say, I mean, in terms of asymptotics, the directions that don't have symmetry, it's compact. So I guess there's not much to say in terms of asymptotics. The motivation and the technicalities behind this converse is, so Ramiro is currently working with Francesco Pediconi on immortal Ricci flows and looking in particular at collapsing ones.
Yep.
And so the converse applies when these arise from collapsing Ricci flows of compact manifolds. Okay, so somehow when you're trying to study and understand geometrically this collapsing behavior, in the limit you unwrap the collapsing directions. Okay, and so the point of our solitons is to model the limits of these collapsing Ricci flows, these unwrapped limits. That's how they arise in nature, so to speak.
In nature, yes. Yes, thank you. Any further comments or questions for our speaker? Well, in that case, let's thank Adam again for taking us through some very interesting pieces of mathematics.
Yeah.
All right, thanks all. I'll stop recording there.